momentum is equal to mass times velocity. That's momentum. Congratulations, absolutely. So a lot of people want to start with conservation of momentum because they've heard that fun buzzword. They're like, momentum is conserved. But it's actually a lot better to start thinking about this when we think about when it's not conserved. So momentum is this. When momentum changes, aka it's not conserved, almost, there we go. I get a change in momentum is equal to a change in velocity times mass. Now, I say that with a caveat. It is possible that I change my momentum by changing my mass. That is possible. However, 9 times out of 10, it's because my speed changed, right? And that looks like another letter for a change in momentum, which is J, which is equal to force times time. So as a reminder, this is change in momentum. This is the effect. This is what happens when I have an impulse. They are effectively equal, but the impulse is the cause. The change in momentum is the effect. So an impulse occurs when an outside force, this force right here, must be an outside force. That's really important. I'm going to put a bubble around it. So a lot of students, when they attack momentum problems, the first thing they think about is, okay, momentum's conserved, and then they do the problem. And then halfway through, they're like, wait a second, was it conserved? Is it conserved? My answer is going to be wrong if it is conserved. Also, or it isn't conserved. Also, all these answers seem wrong based on the fact that it's conserved. So is it? I want you to try and attack momentum problems the other way around. Instead of assuming it's conserved and then finding out that it's not, think about this question. Was there an impulse? Did anything apply a force to my system? That's the question you're asking. Did anything apply an outside force to my system? So when we're talking about two cars colliding in a car crash, I saw one literally this morning after I left the gym. Car crash, it was a T-bone. The cops about 6 a.m. It's not a good day. All right. Car crash, right? If the system is both cars and I say there's no friction, the system is both cars and I say there's no friction, instead of saying, well, would it be conserved? Ask yourself this question. What outside force is doing work on the system or is applying a force over time to this system? All right. Nothing. Okay? The force of gravity is counteracted by the force normal, so there's not a net force in the y direction. And then even as they came into the collision together, if we say there's magically no friction between the car tires and the road, then there's nothing else touching these two cars except the other car. And so momentum is conserved because there wasn't an outside force. Okay? It's a better way to think of it without getting as confused. So let's do another example. Let's play tennis. I like to play tennis. I've been busy, so I haven't gotten out to the courts in a while, but I like to play tennis. I'm not good at it at all. That's a tennis racket. That's what that is. It's not a balloon or a lollipop. It's a tennis racket, I promise. And that's a ball. There we go. So, tennis ball comes towards my racket, bounces off my racket. Okay? I'm going to assume that they go the same speed each way. So it hits my racket going one speed, it leaves my racket going the exact same speed. So your question is, was there a change in momentum? And the way you're going to answer that is by asking the question, was there an outside force? So if the system is just the tennis ball, which I've magically lost mine, but if the system is just the tennis ball, was there a change in momentum? Absolutely. What did the outside forcing? The tennis racket. The tennis racket was external to the system, so it applied a force over a period of time to that object. So there's absolutely a change in momentum. Even though the speed was the same, remember the sign for the velocity changed? Maybe it was going 10 meters per second in, negative 10 out, so that would include a change in momentum. Okay, let's change the system slightly. Now the tennis racket is inside of the system. So now it's a ball tennis racket system. So it's the same question. Was momentum conserved or was there an impulse? And the thing you're asking yourself is, well, was there an outside force? Now, we're going to do this two ways. We're going to make the first example assuming the initial and final velocity of the racket is 0 meters per second. The initial and final speed of the racket is 0 meters per second. So we're thinking about this in terms of, is there an outside force? Is there an outside force? If so, what is it? What applied this impulse to the tennis racket? What do we think? Was there a change in momentum? Was there an impulse? Was there anything touching the racket? Yes, who was touching the racket? Me! I was touching the racket. So then the question is, did I apply a force over time? Well, if we think about it, the initial momentum of the tennis racket is what? The final momentum of the tennis racket is what? The ball still had a change in momentum. So this system still had a change in momentum. So yes, there was an impulse. Me, applied a force to the tennis racket. So I was the impulse in that statement. This would be the same thing if I threw the tennis ball at the wall, right? If I included the wall in my system, that would be weird. Normally you wouldn't. But if I included the wall in my system, there would still be a change in momentum because something held that wall in place. Something made sure the wall didn't move. Large quantities of friction, tension, whatever you want to call it, but something caused that wall not to move. What if instead I assume a scenario where there is an initial velocity of the racket. Initial velocity is positive of the racket. It's going that way. Is that to the left? Yes. Okay. Negative. And the final is positive. So this is actually what really happens in tennis, right? We don't just stand there holding a racket. That would be a very different game. You just hold a racket in the air, see if a tennis ball hits it. That would be a very boring game. Instead, you aim for the tennis ball and you swing. You move your arm, you swing. So it comes with an initial velocity and ends with the final velocity. There is an exact amount that those things could be, where I could get the initial velocity of the ball plus the initial velocity of the racket. We'll call that racket. And the final velocity of these things. I think the hardest part about momentum is remembering which letter to write, I or F. I think that's actually the hardest part. I could get this statement to be true. I would have to be a very specific speed for the ball and the racket, but I could get this to happen. There's a math that makes this go. So it is possible. So those are 3 different scenarios. It depends on how I define my system, but the most important thing to think about is, did an external force do work or do apply an impulse to that system? One thing you probably don't think about, but I also want to show you, and we're going to talk more about it with examples in next class. There's one equation at the very, very bottom of this equation sheet that you've never seen before, I guarantee. It is an equation that looks similar to something higher up. It is the velocity of the center of mass, which is equal to the momentum divided by mass, or equal to m times v divided by total mass. So just like the center of mass, which is m times location, this is the center of mass velocity, which is m times the velocity. So if I have the ball and the racket as my system, when the ball's approaching, what's happening to the center of mass of this system? Let's say it starts closer to the racket because the racket's heavier. What happens to the velocity of the center of mass of my system? Where is that center of mass moving to? Is it moving towards the ball or towards the racket? Towards the racket. The ball's getting closer to the racket, so the center of mass is going that way. When the ball leaves the racket, again, this is assuming the racket's not moving, if the racket itself doesn't move. When the ball leaves, the center of mass is going to leave from near the racket and go out this way. So the velocity of center mass changes. Another thing that proves that there was a change in momentum, because velocity center, the center of mass is constant if momentum is conserved. So this is another way to check. If you're like, okay, I've thought about what the initial momentum and final momentum is. I thought about if there were external forces. I'm still not sure if there was a change in momentum. Check the center of mass velocity. When the racket stays still, the ball gets closer, so the center of mass is getting closer, and then when the ball leaves, the center of mass is leaving. If I'm moving the ball, or the racket, at the exact right swing, so I swing this racket at exactly the right thing, there's a way that I can swing it where, since the velocity of this object's this way and the velocity of this object is this way, I can get the center of mass to stay in the same spot. It'd be tricky, but I could do it. I could get the center of mass to stay in the same spot. Then when they separated and the ball was going back out this way and the racket was going out this way, I could again get the center of mass to stay in the exact same spot, and I could get momentum to be conserved. I feel like that's impossible. I'll prove it. What if I had an explosion? This is a bomb. It looks like a shopping bag. I don't know what I was aiming for a bomb. I haven't seen a lot of them. But that's a bomb. That's like the wire that you cut. Yes.
Wait, what is constant if the momentum is constant?
The center of mass velocity. So, if this is an explosive device, the center of mass of it is in the middle. We all agree, right? To begin with. If this thing explodes and turns into chunks, we know from last year that the center of mass, the momentum is conserved. We can see this again because as all those pieces fragment out and explode, what happens to the center of mass? It stays in the same spot, right? This is the same thing. If I move perfectly between the racket and the tennis ball, I can make that an explosion. The two masses move away from each other at relative velocities, and I can make the center of mass stay in the exact same spot, okay? When I have two cars collide and stick together, so these are my cars, they're going to collide and stick together. So they're headed towards each other, right? The center of mass, maybe this one's driving faster. So the center of mass of these two objects is moving this way because that car is going faster. So the center of mass of the objects is going this way. If this one's faster, we're assuming the same mass. If this one's faster, and this is a completely inelastic collision, when these stick together and move off, which way are they going to go? So which way is the velocity of the center of mass still going to be going? That way. So velocity, center of mass velocity, is another great way to figure out, was momentum conserved? So what I want you to think about as you work problems is momentum actually conserved? Last year, you probably did a lot of momentum problems where it was like, yep, momentum's conserved. Let me figure out this collision. Let me figure out which way the billiard ball went. Okay? That's awesome. But you're going to find that in AP Physics C, the thing that they focus on a little bit more is, was momentum actually conserved? And figuring that out. Versus in AP1, it's a focus on collisions and then on the concept that we wear seatbelts to save our lives. Because seatbelts do what to the impulse? What do they do to the impulse? They change something about the impulse. The amount of the impulse can't be changed because I'm going to come to a quick stop. But me and myself, instead of the car, because I have a seatbelt, how long is it going to take me to actually come to 0 meters per second? Longer. And that going forward and coming back, taking longer for me to come into a 0 meters per second is going to save my life. And that's why I wear a seatbelt. So, all about T. That was more in AP Physics 1. When you see the questions for this one, you're going to be like, okay, but wait, was it conserved? And I'll prove that with one example in just a second. There is, just like with work and change in potential energy, there is a integral that I can find in here, right? This would be valid if the force is constant. What if the force isn't constant with respect to time. Oh no. So then my impulse, J, would be equal to the integral of force with respect to time. It is very important that you pay very close attention to this equation because it is so incredibly similar to the work and change in potential energy equations. What is the only difference between this and the work integral?
Time and position.
Time and position. I integrate one with respect to position. I integrate this one with respect to time. Okay? Just like I did for change in potential energy, I can take the derivative of both sides of this. Well, yes. And I can get that force is equal to a change in momentum over a change in time.
Whoa.
Whoa, what? J is equal to a change in P.
Oh, then not just J.
Because P is actually the thing that's changing. The impulse describes a change in momentum. The impulse itself can't have a change. There was an amount of the impulse. So it has to be change in momentum. So instead of using J, they switch it back to using delta P. But since it's a derivative, it's dP because that means we're taking the derivative, making our limit 0. Yay! So, force would be the derivative of momentum with respect to time. Let's try out a problem real quick. The velocity of an object experiencing a resistive force, so friction, is V is equal to 3t squared minus 2t. What is the change in momentum with respect to time? What is the change in momentum with respect to time? You're like, well, I don't know. They gave me velocity. I don't even need velocity. Velocity isn't anything. Well, it's a lot of things, actually. So if my goal is to find a change in equation for change in momentum with respect to time, I'm looking at this integral right here because that is impulse or change in momentum. On Mo.
Is an explosion just like any interaction where like the center of mass
Stays in the exact same spot? I would say so, yeah. You can consider anything where that happens an explosion. Traditionally defined in like outside of a specific class, it would be defined as, yeah, don't go back. Like actually an explosion. But yes, anytime the center of mass stays the same place, I would say yeah. All right, so if I want to theoretically solve for this impulse here, I need force. I have velocity. That's no good. How am I going to get force from velocity? Anybody got any ideas? Yes? What is the derivative of velocity? Acceleration. Oh, that's very nice. So the acceleration of this, if I take the derivative, is 6t minus 2. So force is equal to what? Mass times acceleration. M times 6t minus 2. Hey, so force is equal to 6mt minus 2m. Cool. That's great. Now I've got force. So now all I have to do is take the integral. So J is equal to the integral from 0 to some time t of 6mt minus 2m. The m's are constants, so you can pull them out if you would like to. That's perfectly fine. So I'm going to integrate with respect to t. This is going to be fun. So, wonder what this gets to. Anybody noticing something? Anybody noticing something? Sorry, I didn't mean to put a 6. I meant to put an M. Whoa, what did I get? It's okay. I got back to the velocity equation. I instead this time have mass times the velocity. But what does this actually represent? It's not just velocity, it's the change in velocity. So I went through an integral. I didn't have to. Change in momentum is also m times change in v. If I assume my initial velocity is 0, then I would get the same answer if I had just stuck the equation in there. I want to show you this just in case you have to do the integral for some reason that I don't know. But you can absolutely just have done that as well. All right, the last thing I want us to think about. Last thing, and it's something I'm going to have you think about and come back next class. We are not answering this question this class. I want you to seriously consider what I'm putting in front of you here. I have a train car. It is on a train track. It's got some velocity in meters per second. I don't know what it is, but it's going forward. It has some very large mass. This is a train car. Now, I'm going to make the assumption that this train car has been disconnected from the train. So there's nothing actually forcing it to go anywhere. It's also magically frictionless. So this train is going to keep on going at its current velocity forever. It's just going to keep on keeping on. However, this is a spy movie or something, and I'm trying to hide a large bucket of gold. I don't know, something. And I've decided I'm going to drone drop this bucket of gold into this train car. So I'm going to set it directly on top. It's little mass m. I've droned it over, and then I've matched the drone speed with the train, and I just slowly lowered down this box of gold onto the train car. My question is, did the momentum of the train car change or not?